Traditionally, people think of cybersecurity as defending the internet and buffer overflow attacks and attacks on software itself. No one really thought about the hardware layers that sit below the software layers.
What our laboratory focuses on are those future threats. Threats against autonomous vehicles, threats against our healthcare system, threats against the Internet of Things.
That is one of the major reasons I came to Michigan, was to study these vulnerabilities in hardware components that are not protected by traditional software means. Accelerometers and other motion sensors are found in consumer devices such as smartphones, Fitbits, smartwatches. Sensors are designed to measure specific environmental signals.
What we look at in my lab is, well, why are those readings considered trustworthy? And how could an adversary actually change those settings to cause harm?
What we've managed to do is basically control the measurement of accelerometers. That is, we let sensor to output any chosen measurement that does not reflect the real motion.
Professor Wenyuan Xu is a longtime collaborator from the University of South Carolina in China, and she works with us on the hardware side as well as a lot of the signals and systems and understanding the physics of analog cybersecurity.
In our case, with accelerometers, the environmental stimuli that we are trying to spoof is acceleration. We do that via acoustics.
Acoustic disturbance can also cause displacement of this movable mass inside accelerometers.
In the laboratory, what Tim does is he creates an automatic system to deliver sound waves at different frequencies to different sensors, and he's able to measure for each sensor their susceptibility to this malicious acoustic interference.
To demonstrate this, I attack a MEMS accelerometer in a smartphone that is running an application that steers an RC car. In another demonstration, I show how it is possible to spoof thousands of steps on a Fitbit without ever taking a single step. We were able to not only disable systems with acceleration sensors, but we could control their output in a way that would alter the behavior of systems that use these devices. By applying a specially crafted acoustic signal to a vulnerable MEMS accelerometer, I can achieve a desired output waveform from the sensor. For instance, I demonstrate spelling out the word walnut from the output signal of an accelerometer by using only acoustic interference.
So for output biasing attacks, we utilize the signal aliasing phenomena. So according to the sampling theory, the sampling rate has to be at least twice of the maximum frequency of these analog signals. We can use two ways to control how much DC output we want to create. One is using the amplitude modulation, the other using phase modulation.
We, as researchers, are not trying to exploit vulnerabilities for the sake of causing harm, but rather for the sake of improving the safety and reliability of the systems that we use every day that contain vulnerable devices.
So one of the innovations from this work on acoustic interference is that we've discovered how to create software that can defend against many of these attacks.
We contacted the manufacturers of the chips that we studied in order to help them manufacture more secure and reliable sensors in the future.
We hope that the industry will be able to use our software techniques to retrofit security into their already deployed products. The end game here is how to make our embedded systems more trustworthy. Once we can solve a lot of these problems in analog cybersecurity, we believe consumers will have more trust in emerging devices.